Well, it's 9:30. Good morning, everyone. We still have a lot of procrastinators that they're always going to be late. Let's see. I have 12 people missing. Uh, we're going to do a couple of things before we continue on diesel cycle. Number one, I need 7 names to be the project team leader. 7 volunteers. And
I'll volunteer. My name is Arthur.
Arthur. All right, that's one. Who else? Oh, I'm sorry. I need 6 more. And two of the ladies also.
I'll volunteer, Professor. Blake?
Blake?
Yes.
Okay. Let's see, Blake. All right. 5 more. Come on, guys.
I'll volunteer.
All right,
Abraham Serrano.
Abraham. Okay. One more.
Professor, I don't mind.
Okay.
Hytham,
What's your first name?
Hytham, Haytham.
Okay, where are the ladies? Come on, don't make me volunteer you. All right. So you don't want to volunteer on your own? Okay, let's see. We'll find 2 more. Here's our 17 members. Now, before I forget, let me take a picture of this. All right. All right. These people, these 7 people, going to be the team leader. This is your future because when you graduate and you have a project and you're assigned to lead the project, they call you project manager. So these are the list of the project managers. We talk about your responsibilities, what you need to do. And I'll send you all the information, so nothing to worry about. The project is very easy. What I need you to do, these 7 people, I want you by, let's see, by Monday or before that, hopefully before that. I want you to email me the list of people in your group, including their name, email address, and phone number. So you put your name first as a team leader and 4 other guys to make it 5. All the way through. There's only one team that's going to have 6. Everybody else is going to be group of 5. Because we have 36 people, so we have 7 times 5 is 35. But one group get lucky, have an additional person. Everyone, there's no exception, must be part of this project and must be part of one of these teams. I'm not going to tell you who's going to be on your team. You decide, you talk to your classmate, pick your team members and put them together, send me a list. Hopefully by Monday, I will have 7 emails with the list of all people going to be involved. Once I get that, I will assign the project to you. Then at the end of a class, I will email you the list of the projects. Then you know which one is project number 1, which one is number 6, which one is number 5, and that's the one is assigned to you. You will have all. And then the following Wednesday, I'm going to spend 15-20 minutes talking about the project and how you should approach it and how you should do it. As I mentioned, you're going to have plenty of time over 2.5 months to do the project. So there's no excuse that you didn't get a chance or you were busy or any of that. Most likely you're going to end up to work average of 15 minutes a day, even less. So it's not going to be that big of a deal. All right? Any questions? Do all these team leaders know that what they need to do?
So just to clarify, Professor, it's 4 plus 5 total. So the group leaders will recruit 4
Yeah,
members.
exactly. Every team leader going to recruit 4 people, including himself or herself, is going to be 5. There's only one group that they can have 6. I don't know which one is going to be. So that's all up to you. So if there are 2 groups of 6, that means it's not going to work because one group has only a total of 4 people. So try to have 5, and then there will be one person running around to be in part of any group, and then you pick that person. So we're all set. Any other questions? So again, Arthur, Blake, Abraham, Peyton, Richard, Wu, Jacob, and Joel. These are the 7 team leaders or project managers. Are all these people here? I assume they are. Let's see. We're still missing 2 people. Is Joe here? Joe?
Yeah, I'm here.
All right. Jacob? I saw your name. Jacob,
I'm here.
good. Richard Wu, you're here. Peyton is here, Abraham is here, Blake is here, and Arthur is here. Okay. We're done with that. So let me erase this. Now, I need you to do yourself a favor. If you recall last time, before we started the diesel cycle, we did an example of auto cycle problem. And we solved the problem thermodynamically because Cp and Cv were not constant. Now let's solve the same problem assuming Cp and Cv are constant. I want you to exercise that. Do that on your own. This is not a homework assignment or quiz or anything. Just want you to do yourself a favor. Do this exercise on your own. It will take you probably 5-6 minutes. And compare the answer you get with what we did in the class. And see what are the differences. And you notice the differences. And that's a great deal. I want you to exercise that because you never know on a test, you might get Cp and Cv constant. I don't want you to say, oh, no, God, now what I'm going to do. And especially next, topic, which is basically, or even Brayton cycle. You might see Cp and Cv are constant. If you don't practice this, you're going to get lost. Let me run over that, even though I did it before, but I still want you to do this. The same problem. The R of V was 8. The temperature at point 1 was 27 degrees Celsius, which is 300 degrees Kelvin. Pressure was 95 kilopascal. And this time we are assuming that Cv and Cp are constant. Now, in the problem we solved, they give us the Q in. And that's how we found all the other values. This time, instead of a Q in, I will give you temperature at point 3. That is 1540 degrees Kelvin. So with that information, you need to find the same thing we did. Now, how we're going to do this is a crucial point. That's very important that I told you to read the problem carefully and slowly. Once you see that, you know that you can use the heat transfer method to solve the problem. And what is that? We have equation for ideal gas isentropic processes. That means T2 over T1 is equal to V1 over V2 to the power of K minus 1, or R of V to the power of K minus 1. From there, you find the value of T2. Similarly, T4 over T3 is equal to V3 over V4 to the power of K minus 1. And we prove that V3 over V4 is 1 over R of V. Reverse of that to the power of K minus 1. From there, you can find the value of T4. Now that you have that, the rest becomes easy. The queuing is in a constant volume process. It would be CV times T3 minus T2. The Q out also is in a constant volume process, going to be CV times T4 minus T1. Quick as that, as simple as that. The difference between the two, as always, Q in minus Q out, would build the network. Our thermal efficiency never changes. Network divided by Q in, or 1 minus Q out over Q in. And our MEP remain the same, which is a network divided by V1 minus V2. And we can find V1 from this equation. Once you find that, because of this relationship, you can find the value of V2 and consequently you find the value of MEP. You can see the same problem that took us more than a half an hour to go back and forth on the table, do a lot of interpolations, which you didn't do, I already did that, to find the answers. But if you look at this, there is no table involved. There is no interpolations. Very quickly, very straightforward, 1, 2, 3 step, 4 steps, you can solve a problem. Simple as that. I want you to practice this with the same condition you had before. Now I want you to find out what are the differences on the thermal efficiency. Once you find the Q in, is this the same Q in that we had on the last problem? What's the MEP value? Is it the same or bigger, smaller? What is it? So do yourself a favor, do this exercise, do this practice, because you're going to see this over and over, and most likely will be part of your test. So we advise, please, don't take it lightly. Any questions on this?
Just give me one more minute just to finish writing out.
No, that's quite all right.
Thank you.
These are called ideal gas equation for isentropic processes. 1 and 2 is isentropic, 3 and 4 is isentropic. You cannot use it between 2 and 3 and 4 and 1. Be careful. These are called heat transfer method of solving a problem rather than thermodynamic, because thermodynamic we find H values, U values in order to solve the problem. Once you find Q in and Q out, the rest of them, it doesn't matter how you find the Q in and Q out. The network, the thermal efficiency, MEP, they all remain the same. How you find these two are important. Done?
Yes, thank you.
All right. Now, let's go back to what we started, and that was diesel cycle. I'm not going to draw the equipment diagram because you've seen it 3, 4, 5 times already. That will not change. In the diesel cycle, if you remember, we said we only use PV diagram, not the TS, because we don't need it. So process 2 to 3 is a constant volume. I'm sorry, constant pressure, and process 4 to 1 is at constant volume. Once we identify this, connecting that gives us the PV diagram. Not to forget, process 3 to 4 is isentropic, obviously, and 1 and 2 are isentropic. I make a dash line so I don't forget. Now, once again, this is the work of a compressor, or work we put into the system. This is work of a diesel engine. That's work we get out of the system. This is when we reject heat or Q out. And this is when we add heat, which is Q in. Just to refresh your memory and redoing that. Now, if you remember, the reason we have this, because process 1 to 2 is isentropic. That's given. All compression, expansion, isentropic. The only changes that diesel did, change the process 2 to 3 at isobaric, which is constant pressure. Process 3 to 4 remain the same, isentropic. Under no circumstances, processes for compression and expansion will change. They always remain isentropic. Regardless of the cycle, regardless of what you do, that always chapter 9, 10, 11, you have these compression and expansion as isentropic process. The only changes happen in these two processes, Q in and Q out. Now, if you remember, Otto cycle, Q in was constant volume, Q out was constant volume. But here, he changed it to constant pressure. Again, 4 to 1 is isochoric, which is V1 is equal to V4. These are the processes, and based on these processes, we drew the PV diagram. Now, we said as far as the quantity is concerned, work in is a delta H across the equipment. I make it H2 minus H1. Work out is a delta H across the equipment, H3 minus H4. Q in is at constant pressure. Going to be delta H across the combustion chamber, H3 minus H2. When it comes to Q out, now we have constant volume. That would be U4 minus U1. These are the quantities. As always, the difference between these two or the difference between these two will give you the method. That will never, ever change. So, network is Q in minus Q out, or work out minus work in. Either one. Depends. If the problem asks you to find a work in and work out, find a network that way. You don't have to, do the extra work. If the problem wants you to find the Q in and Q out, find the network this way. Just stay away doing your extra work. Finally, the thermal efficiency, once again, it's a network divided by Q in. That will never change. These two always stays the same. You're going to see that over and over and over. So this is the quality, these are list of the quantities of energy around the cycle. Any questions so far? Because we went over all of that. Just trying to refresh your memory. Now, let's talk about characteristics of diesel cycle. Number one, we have a compression ratio. Again, R of V is V1 over V2. Maximum volume divided by minimum volume. V1, which is here, and V2 is right there. V3 is going to be here. So maximum volume is V1, minimum is V2. V3 is somewhere between these two. So that is our compression ratio. You've seen this before in other sites. And also, you saw the relative volume at a given point. Which is V of R1, V of R2, V of R3, and V of R4. So far, everything you see here, you saw in our cycle. We also have relationship between the relative volume and compression ratio for isentropic processes. VR1 over VR2 is the same as V1 over V2. Now, similarly, VR3 over VR4 is the same as V3 over V4. Now, this is where we have issues. We already have V1 over V2. Problem gave us the compression ratio. We don't have the value of V3, we don't have the value of V4. So we need to work this out. This is not a reverse of V1 over V2. Look at it. V1 over V2. Now you have V3 over V4 because these two are the same. So this portion is not the reverse of that. You see that very straightforward in the diagram. So we need to work that out. And we come back to it, how we're going to work this out. Now, the important characteristics of a diesel cycle is called cutoff ratio. And we show that as R of C, cutoff ratio. Now, what is a cutoff ratio? By definition, R of C is the volume at the end of heat addition divided by volume at beginning of heat addition. Now let's see, we go back to our drawings, our diagrams. What is the end of the heat addition? That's V3. What is the beginning of a heat addition? It's V2. So actually, R of C is equal to V3 over V2. All right. Now, once again, we need to explore this to see what's going on here. Now, if you look at this carefully, I don't have the value of V3, and I don't have the value of V2. I have to find a way to find this value. What's the best way? I will use ideal gas equations again. P1 V1 over T1 is P2 V2 over T2 is P3 V3 over T3 and is P4 V4 over T4. That's true through the entire cycle. I'm looking at this. I don't need that. I don't need that either. I'm going to stay focused and right in the middle. I have P2 V2 over T2 is the same as P3 V3 over T3. Now I'm looking at my diagram again. I notice that P2 and P3 are the same. So let's see, I cancel that. If I cancel that, what happens? I will have T3 over T2 is equal to V3 over V2. See how simple it is? So I use ideal gas equation, and when I look at it, I know that P2 and P3 are the same, they cancel each other out. Now, T3 over T2 is the same as V3 over V2, right there. So cutoff ratio in reality is a temperature at the end of a heat addition divided by the temperature at the beginning of heat addition. In diesel cycle, you cannot solve any diesel cycle problem without cutoff ratio. Absolutely not. So this is very important to have. Remember this. So that was for the cutoff ratio. Now let's come back and explore this situation, V3 over V4. What can I do to that? All right. I'm looking at this. How about if I first write V3 over V1? Why? Because V1 is equal to V4. V3 over V1. So far, so good, huh? Now, if I divide the numerator and the denominator by V2, what I'm going to get? I'm going to get V3 over V2 divided by V1 over V2. Looks familiar? V3 over V2 is R of C. V1 over V2 is R of V. What was it? Right here. So in reality, every time I see V3 over V4, I automatically replace it with R of C over R of V. That's why you cannot solve any diesel cycle problem without having a cutoff ratio. Because when you get here, you get stuck. You don't have the value of V3 and V4. So please pay attention to this. These two are very important in solving the diesel cycle. When we start actually solving the problem, you'll see that. Any questions? Now, keep in mind, diesel cycle going to be on your next test and definitely is going to be on your final exam. So this is very important for you to learn. If you understand what I wrote here and comprehend that, then you're home free. Every semester I give the first test, a lot of people automatically assume that V3 over V4 is the reverse of V1 over V2. That's not true. It was true in the case of an auto cycle, but not in diesel cycle. And the graph is a proof of that. That's why I went out of my way to prove it to you that this relationship is equal to R of C over R of V. Be careful on that. Now, when you want to solve the problem thermodynamically, we go around the cycle, we find H values and U4 and U1 values. That's how we find Q in, Q out, net work, and ultimately thermal efficiency. In diesel cycle, we also have MEP, which you have seen before. Same definition, net work divided by V1 minus V2. And you find V1 through this equation. So once you find V1, V2 would be V1 over R of V, whatever that compression ratio is. Because you're using this relationship. Once you find one of them, you can find the other one. So you've seen the MEP, nothing's changed there. The two important parts of a diesel cycle are these two. The other part is this diagram. Without this diagram, you cannot solve any problem. So that's the thermodynamic way. What happens is if Cp and Cv are constant, how are we going to solve that problem? That becomes very easy. Now, if Cp and Cv are constant, once again, we use ideal gas isentropic equation. Again, T2 over T1 going to be equal to V1 over V2 to the power of K minus 1, which is R of V to the power of K minus 1. Now, T4 over T3 is V3 over V4 to the power of K minus 1. And we prove that it is equal to R of C over R of V. So that would be R of C over R of V to the power of K minus 1. Once you find all these values, you have T1 and T3, you found T4 and T2, then your Qing would be Cp times T3 minus T2. And your Q out would be Cv, because it's constant volume, times T4 minus T. It doesn't matter how you find the Q in and Q out, the network relationship stays the same, thermal efficiency stays the same, MEP values stays the same. But you can see how fast and quick you can solve this problem rather than going to headaches of finding H values and U values around the table. Any question? Now, I want you to be aware, most of the time, the problem doesn't tell you straightforward that consider CP and CV constant or assuming CP and CV constant. They play tricks on you. For instance, as you know, the value of CP and CV, write it here. You know that CP is function of temperature. Of course, function of time, but let's just stay focused on the temperature. So as the temperature changes, these values are going to change. So under normal circumstances, never ever CP and CV will be constant. Never. That's a real life. But sometimes we make that assumption and we say, okay, CP and CV are constant. We go through this process to quickly come up with an answer. The reason for that, we want to get a ballpark figure, tell the customer first, and then when we were assigned to do the actual work, we don't go that way. We do it the hard way, going through the tables, because that's how we can find the actual values. That's the reason we make the assumption. However, there are tricks. If they are not constant, they will say, considering variable CP and CV. What does it mean? CP and CV are not constant. It says variable. That means there's variable temperature. Now, they come in and say, assume CP and CV at the room temperature. They don't tell you it's constant, they say assume at room temperature. What does it mean? That means this temperature stays the same at all times, room temperature. That means CP and CV are constant. That's why you need to read the problem carefully, think outside the box, use your talent and smart engineering analysis and processes to comprehend. Stay away of being a student anymore, that everything has to be in a silver platter and handed to you so we can reach out for your gun, in this case, your calculator, and start crunching the number. Stop doing that. You're too smart not to use your brain. Come on. Stop being, just a student. This is the course you're going to be trained for that. Sometimes the problem says, assuming CP and CV at 300 degrees Kelvin. What does it mean? 300 degrees Kelvin is 27 degrees Celsius. That's ambient temperature. Again, they're telling you that CP and CV are constant. So that's why it is so important to read the problem carefully, slowly, trying to understand it, rather than jumping right into it. Any question? Couple of more things. there's an equation in your textbook, and it's called equation 9.12 or 9-12. And this is an equation under these circumstances only. CP and CV must be constant. You can find the thermal efficiency through that equation. And that is 1 minus 1 over R of V to the power of K minus 1 multiplied by R of C to the power of K minus 1 divided by K times R of C minus 1. This is called equation 9.12. That means if you have R of V and R of C, and this condition exists, you can bypass all of this process and find the thermal efficiency in one shot, one step. Without going through any headaches. So this is on your textbook. Don't try to memorize it. You have to use it. Look it up. Any questions? I'm getting worried. Any questions? Okay. Let's see. I want to talk about a couple of things. Remember this. In a problem for diesel cycle, you either given R of C, if this is given, then you will find the value of T3. Or T3 is given, you will find the value of R of C. You have to have that in order to solve a problem. So if T3 is given, first you go find, you have T1, so you find T2, whether to CP and CV being constant, or using a table. Once you find T2, you divide this by T2, you get a cutoff ratio. If you have that, you multiply this by T2, you get T3. So T3 is equal to cutoff ratio times T2. And a cutoff ratio, of course, you know, is T3 over T2. So you always have to have one of those. You can have one equations and two unknowns. So if the problem was giving you the R of C, it means you need to find temperature at point 3. If the problem gives you the temperature at point 3, that means you need to find R of C. Don't forget that. Now, one of the mistakes that I see every semester on a first test is people using ideal gas equations to find the temperature, even though CP and CV are not constant, which they're not allowed to do that. And then they find H values and U values. That's a big no-no. You need to work in one system, either heat transfer system or thermodynamic system. If you start with thermodynamic, even though if Cp and Cv are constant, you can still use thermodynamic. Use the tables. Your choice. You either have to stay with that or go and do it heat transfer way. You can mix and match. Absolutely not. Once you do that, every work that you did from that point on is all garbage. You get absolutely no credit. Remember to stay with one system. If Cp and Cv are constant, use the ideal gas equation, find the temperature, use the heat transfer equation. Don't even bother to look at tables and find a value of H and U or anything else, because you don't need to. If Cp and Cv are not constant, don't even think about using this equation or any other equation to find the temperature. The only way you can do that, going through the thermodynamic process, which once we solve a problem, you get the hang of it. So it is important for you, not only for diesel cycle, also for Otto cycle, also for next one, which is Brayton cycle. All of that, you need to stay in one system and one system only. Do not cross them over. That is the biggest mistake you can do. Avoid that, please. Any questions? No questions. Okay.
So Professor, just to clarify, like all the formulas that we've written since you started talking about the diesel cycle is using constant temperature and volume, or constant pressure and volume, like Cp and Cv is constant?
No, when we started, Cp and Cv were not constant.
Okay.
We have to use the table the same way we did it on Otto cycle. We had a temperature, we went to a table, we find U1 and VR1 through relationship of a V1 over V2 is a VR1 over VR2. We find H2, as you see, and also T2. Once we have T2, if we have R of C, we find T3. Then at T3, we find a value of H3 and VR3. Then we go put it in a VR3 over VR4 is a V3 over V4 situation to find VR4. From there, you find U4. Now you have U4, U1 for Q out, H3, H2 for Q in. And that's how we can find it, network, thermal efficiency, MEP, and so on. However, if Cp and Cv are constant, then we don't have to go through that headache. We use just the temperature and heat transfer equation. That's what I did right there.
Okay, got it. Okay, thank you.
No problem. Now, one thing I want you to be aware, there are some man-made, cycles that has nothing to do with Otto cycle or let's see, diesel cycle or any other cycle. Those man-made cycles are specifically designed for you to learn how to do the TS and PV diagram based on the information you have. For instance, let's say somebody come in and give you these processes. They're not telling you this is, the auto cycle or Carnot cycle or any cycle. There's just a process 1 to 2. Isentropic work. Process 2 to 3. Isobaric heat addition. Process 3 going back to 1 is isochoric heat rejection. As you can see, I'm making this up. This is not the real cycle. So it has only 3 points. They ask you to find the TSM PV diagram. Let's see if we can do this. Whoops. So I'm going to look at this. I have only one isentropic process, 1 going to 2. 2 to 3 is isobaric. That's 2 and 3. 3 going back to 1 is isochoric. That means I come down here to 1. That's all I have. To complete my PV diagram, I know from 1 to 2, I'm going exponentially high. So this is my curve. And that is the isentropic quantum. This is the cycle they asked me. Now here, I look at that. From 2 to 3, I'm adding heat. That means I go exponentially up, temperature. Then I drop to 0.1 exponentially. So there we go. This is a man-made cycle. Doesn't exist. I just, right in front of you, made it up. This is designed not for you to do anything, but just learn how you can develop TSM PV diagram. Now, you guys give me some processes, whatever you want. Let's see if I can do this. All right, somebody tell me process 1 to 2.
Isobaric.
Isobaric, okay. Constant pressure. P1 is equal to P2. Process 2 to 3.
Isentropic.
What?
Isentropic.
Isentropic, okay. S2 is equal to S3. All right. You can have 3 to 4, 4 to 1. You don't have to have only 3. Tell me whatever you think of. You want to say only 3 or you want to go 4?
Let's do 4.
Okay, so what is 2 to 3, 3 to 4? What do you want the 3 to 4 to be?
Isochoric.
Keep in mind, since you have an expansion, I'm sorry, compression, you have to have expansion. So we need to have from 4 to 1 has to be isentropic. Otherwise, it doesn't work. That means S4 is equal to S1. So now we have 4 points. This is not any cycle that we know of. Let's see if we can do this. So we have 2 isentropic, so it's easy. 2 to 3, so I have 2 going to 3, isentropically, and then 4 to 1 isentropic. That would be 4 coming to 1 isentropic. Process 2 to 3, I'm sorry, process 1 to 2 was constant pressure. So 1 going to 2 at constant pressure. Process 3 going to 4 is isochoric. So 3 has to be here coming down to 4. Guess what? You guys almost did a diesel cycle without even knowing yet. So as you can see, regardless of, of course, this is not diesel cycle, but whatever the process is, it's so simple to draw this TS and PV diagram. So for your homework, I intentionally gave you one of these because I want you to practice that. I want you to learn how to do it. And I give you some parameters you need to solve a problem. And you have to use your engineering thought process in order to do that. So please be aware of that. Any questions so far? No questions? Let's see if I have time to do the example for the cycle. Let's keep this. Here's that. So we're going to do an example for diesel cycle. We know that we need the PV diagram. That's 2, 3, 4, and 1. Now, this is the air standard diesel cycle with a compression ratio R of V is 18.2. The T1 is 27 degrees Celsius plus 273, that will give us 300 degrees Kelvin. P1 is at 100 kilopascal. These are all at the beginning, P1 and P1, at the beginning of a compression. Then I said, and at the end of a heat process, the temperature, what is the end of a heat process? Right there, because this is your Q in, and that is your Q out. At the end of a heat process, that means T3 is equal to 2000 degree Kelvin. Now, these are the given. Now it says find A, cutoff ratio. I have the equation right in front of me. B, thermal efficiency, which is the network divided by Q in. Oh, I'm sorry. That's C. B, this is a trick. You need to pay attention. Heat loss per unit mass. What this means, heat loss per unit mass. everything we do here is per unit mass. Where are we losing heat? Right there. That means find the Q out. That's what it means. But instead of telling you find the Q out, they said find the heat loss per unit mass. I said, oh my God, what is that? So you need to pay attention, read it carefully. Now, solution. Once again, we organize ourselves and go from state one all the way through. Now, at T1 is equal to 300 degrees Kelvin, we go to table A17, we find U1. Why U1? Because Q out is U4 minus U1, so I need U1. And VR1. You've seen these numbers before. Oh. So that's one value. I go to state two. At state two, I'm going to write VR1 over VR2 is V1 over V2. This is given 18. $18.2. I already found VR1. So if I divide this by 18.2, I can find the value of VR2. In this case, the VR2 value would be 34.13. Now add VR2 equal to 34.13. I go to table A17. This time I find H2 and T2. Why H2? Because I need to find Q in. Q in is H3 minus H2. Q out is U4 minus U1. So by interpolating both for temperature and for enthalpy, my temperature becomes 901.7 degree Kelvin, and this becomes 934.8 kilojoule per kilogram. Please try to stay with one or maximum 2 decimal points. Don't put 5, 6, 7, 8 decimal points in your answer. So before I go further, I'm going to find R of C. R A is equal to T3 over T2. T3 is given, just found T2. If I plug the number in, I will find the R of C value to be 2.218. So that's very important to have. Now I need to find Q out. That means I have to find H3 and U4. So I go to state 3. At T3 equal to 2000 degree Kelvin, I go to table A17. I find H3 and VR3. Now the value of H3 and find my notes. Oh, that is terrible. what? This should be somewhere bigger than 2000. And I know that VR3 value,
In the table for H3, it says 2252.1.
225,
2252.1.
thank you so much. I don't know how I missed that. I know the VR3 value is 2.776. So that's H2, this is H3. And now, last part is state 4. I write VR3 over VR4 is equal to V3 over V4, and I replace these with R of C over R of V. If I do that, I will find the value of VR4 to be 22.78. Now, I go back to table at VR4 is 22.78. I go back to table A17. This time I will find U4. If the problem asks me, I find T4. If not, I don't bother with it. This problem doesn't ask me that. So my U4 value becomes 788.3 kilojoule per kilogram. So to find the Q out per unit mass, Q out is equal to U4 minus U1. If I plug the number in, I find the Q1 to be 574.2 kilojoule per kilogram. That's part C of the problem. Part B of the problem. Finally, in order to find the thermal efficiency, I need to find the Q in. So Q in is H3 minus H2. I have both values. If I plug the number in, this becomes 1317.3 kilojoule per kilogram. So to do the thermal efficiency, I don't have to find the network. I will write thermal efficiency is equal to 1 minus Q out over Q in. I have the Q out, I have the Q in. So why do I have to bother finding a network? The problem didn't ask me. So don't do any extra work that you're not supposed to do. So if I plug the number in, my thermal efficiency becomes 56.4% as part C of the problem. So you saw how simple it was. If you write all the given information, try to find, like here, 1 minus Q out over Q in, and part B was finding the Q out. So I went to step 1, based on the temperature, find U1 and VR1. Then use this relationship, finding VR2, going to the table, finding H2 and T2. Using this relationship, finding the cutoff ratio of what the problem asked me to find. Now, T3 equal to 2000, I find H3 value and VR3 value. Again, using this relationship, replacing V3 over V4 with RC over RV, I find the value of VR4. Go to the table, find U4. I don't have to find T4. That's extra work that I don't need to do. Part B, the Q out, small q, that's why it says per unit mass, is equal to U4 minus U1. I have U4 and I have U1. Finding the number, this is what you find. In order to find the thermal efficiency, I need to find the Q in. Q in is H3 minus H2. I have both those values. This is what I get. Now, I use simplified thermal efficiency equation, and I find the thermal efficiency. So it's very simple. If you get organized, follow through, you can solve any kind of a problem. Any questions? No questions, huh? All right, well, we're all right at the time, actually 2 minutes past. Thank you, guys. So I'll see you next Monday. And please don't forget to email me and use my work email address. Do not email me to the school email address because I seldom check it out. And sometimes you need something in a hurry and I get back to you a week later. But if you send it to my work email, I respond to it very quickly. With that, have a good day and have a good weekend, and we'll see you next Monday.
Sorry, quick question. Will you be assigning the homework soon? Just want to kind of practice these problems if I can.
Yeah, right after we finish chapter 9, which is we're very close to.
Okay, great.
One more item left on chapter 9. Once we finish that, then I will sign home.
Okay, thank you.
Okay. If you have any other question you want to stick around after the class, fine with me.
Thank you.
No problem. Thank you.